So I just went through a few iterations, and here's the best score that I've come up with so far. It's 84% rounded. Breakup, that's pretty good. I mean, we started with 0. And I'll just give you an indication of what my process was. You can see I have quite a few in here. I checked subsample and didn't get any gains. Now, subsample is for rows, okay? But the columns, it would make sense that, you know what? The columns actually can make a difference here because there's so many columns. So cutting down the percentages of columns would seem to help. So I tried by tree, by node, and by level separately. Got about the same score, hovering around 0.5. Okay, so I tried to tweak that a little, just checking different combinations in the 0.5 range. And I think that's what I decided to peek out at here, say, hey, 75.7%. And then I just checked the learning rate basically and did a better learning rate, which means you may wonder, well, what is the learning rate? Well, first of all, the XGBoost official documentation, you can look it up, XGBoost hyperparameters, read the docs. This is their writings, the people who made this, Tanki Chen. And it's got a lot of great stuff here. And you know, it's a little technical. Okay, so you can also try other readings on them, but you know, if I click on, like, it's also called ADA, see Elias learning rate. You can see that's their default 0.3. That might not be sklearns, but it says the step size shrinkage and updates to prevent overfitting. Basically, it has to do with like each round when it tries to find the minimum error, how far ahead it checks. Like hey, like you have, think of like X and Y. You know, if like X equals 2 gives you a certain error and you're going to check the next one, what number are you going to check? Like 2.1, 2.01, 2.001. That's the idea behind the learning rate. That's with how quickly you can move through values to find better errors. Okay, so, you know, I don't want to like, this lesson is not on like hyperparameter fine tuning. It's included, sure, right? And I think the big emphasis here is that we're doing it on the recall score, right? So this is what I want to do. I want to go back to close this out and just see how we do with these parameters now. If I go back to what we had, right? So if I go back all the way up, don't feel like writing code any more than I have to today. We did this, right? So this was our original model that we used. Now this is, okay, this is not like a final test because we did it separately. And final lessons, we will split it out properly. I'll show you how that's done. Really, you just split it at the beginning and then you wait until the very end and now you check the test it. But we're just going back. This is almost like still testing and saying, okay, made all these changes. We've seen these confusion matrix classification reports with other stuff. What about here? Well, let's put everything in. Okay, put everything in. Scale positive weight 150. One at a time, what you see up there, just give it a try. Max depth equals 1. And estimators, the order doesn't really matter, by the way, equals 60. I should be consistent about if I'm going to use spacing or not here. And the main reason why I'm doing that isn't so much to get the score. It should be hopefully somewhat comparable, but it's to see it with everything, to see the how the other scores changed. The confusion matrix, the classification report, and they'll reveal the precision in F1 scores too. So call sample by level 0.5. Call sample by node is 0.5. By the way, I didn't check gamma. Call sample by tree, 0.5. Or 0.4. And the learning rate, 0.01. 0. I did actually try one more learning rate to see if I could improve it, but it didn't. Okay, let's do a quick check. This looks good. right? And so we're just going to go back and like try it again, basically. Got an error. About syntax, left off a column, comma. It's common. And look at that. So it definitely worked. I'm excited. So to a certain point, right? Like we got what we were looking for, which was the strong recall. Okay. But it shows you another potential disadvantage, which is only focusing on one of these metrics because it was at the cost of everything else, actually. I mean, the precision of zeros isn't bad, but it's only like 4 out of 6, right? So in effect, like it's starting to predict a high number of exoplanets, right? Like too many, really, 57. But again, if there were only this many, then it's doing like an okay job because like the point here was actually to get the exoplanets. But you want to do a little better than just predict everything's an exoplanet. So that can show you why like an F1 score could potentially be like a better bet here. I think what I would do in conjunction with this result, like if I wanted to take this a step further, I would go back and use more data, right? Like I don't want to do that now because it's going to take a lot of time. But we lowered the data like as a technique, but there's a lot more rows in here, so we could actually up the data, and we could probably find a way to show multiple scoring, so that maybe we're not just exclusively focused on the recall score. Maybe we do look at the F1 score. I actually like the idea of exclusively focusing on recall and then using that potentially as a starting point, right? So if I know that these outputs give me a good recall score, I could potentially use those as a starting point then to try to improve the F1 score, okay? And I think hopefully what you can take away from this whole lesson is that imbalanced data is tricky and you have to be really careful when dealing with it. I think the main message got through. Accuracy isn't enough. The confusion matrix and classification report can help you, and you can fine tune your models using different scoring metrics. Thanks.